Welcome to you all. This is lecture number 11 of phase equilibrium module. So, we will just recap the contents of the last lecture before we move on to the next one. So, in this last lecture, lecture number 10, we started our discussion on real solutions. Okay. Now, real solutions are those which do not obey the constraints, such as size differences are not there. In reality, atoms are different in sizes. As a result, you have different strain fields which affect their mixing, and they add basically the enthalpy of mixing. And then they have structural dissimilarity. So, one might be FCC, another might be BCC, and so on and so forth. There may be differences in electronic behavior. For example, they may have different valences, they may have different electronegativities and electronic configurations. So, all these things lead to formation of solid solutions which are imperfect solid solution. They are not ideal solid solution, which means there is not complete randomization as we expect. And also the entropy changes in that case are different as compared to real solutions at different temperatures. So, what you may form is substitutional solid solution or interstitial solid solution, and these may be disordered short with something with short range order or completely ordered. Okay. So, depending upon various factors, solutions may be disordered, they may be short range ordered, they may be long range ordered. So, and they may form various phases. These phases could be intermetallics, they could be ordered phases, and variety of other phases. Okay. And we also described a parameter called as S, which was basically the difference of observed number of AB bonds minus PAB random, then what is the maximum number of PAB bonds if it was completely ordered, and then again in a random solution. So, basically if you had if you had S being equal to 0, that means AB was equal to AB random. In that case, number of bonds are same as in the random solid solution, which means there is a tendency for randomness. So, you can have S to be equal to 0, which is completely random solid solution, very close to real scenario, but that does not happen in most cases. Or you can have other scenario which is S is equal to 1, where number of AB bonds is same as the maximum number of AB bonds that you can have in an ordered solid solution. In that case, it will become equal to 1. So, this is completely ordered, and this is possible. This is found in various material systems. And then you can have intermediate S, that is S less than 1 greater than 0. This may say short range or partial ordering, and this is seen in this is possible in a variety of solid solutions which are although disordered, but they may be partially ordered. So, we took example of, for example, in copper aluminum system goes from disordered state to CuAl ordered state as the temperature decreases. So, temperature decreases. So, across below a certain temperature, it becomes a ordered solid solution. Above a certain temperature, it becomes disordered solid solution. You can see that When it is disordered, then delta S mix, which is driven by configurational entropy, is high, whereas in this case when you have an ordered solid solution state, in this case delta H mix is low. So it is, so if you look at delta G mix is delta H mix minus T delta S mix. So it is the competition of these two terms which determines which phase will be stable at which temperature, and it turns out at high temperature the minus D delta S mix term wins over the delta H mix term. As a result, disordered phase is more stable, whereas at lower temperature the delta H mix term dominates over minus T delta S mix. So decrease in delta H mix is higher than increase in than the lowering of this term as a result of reduced entropy. So as a result, delta G mix is lower for ordered systems. So this is what happens in case of real solutions. You can have complete ordering, you can have incomplete ordering, you can have partial ordering. So now let us begin this lecture with discussion on what are these other phases. So let us first begin with, let us define as, intermediate phase. So as the name itself suggests, the intermediate phase is the phase which forms somewhere in between at the composition range when they are not able to form solid solution all throughout. So for instance, A and B may have dissimilar structure, or they may have, so you may have to recall the module 1 structure of materials where we discuss the formation of solid solutions, or they may have size difference beyond what is predicted by Humo 3 rules to form a solid solution, or they may have excessive differences in the electronegativities. So these differences may lead to formation of, so these will prevent formation of an extended solid solution across the composition range. As a result, they form phases in between. So if you consider pure A and pure B, so let us say this is the composition space, this is A, this is B, and this is, let us say, temperature. So on this side they may form solid solution of B in A. On this side they may form solid solution of A in B. Somewhere in between they may form, either these two solid solutions may coexist or they may form intermediate phases which are different to solid solutions. So that is a possibility that may occur in material systems. So some of these phases, intermediate phases may have, so there are various kinds of intermediate phases that can form. For example, there could be a phase with a fixed atom ratio which results in lowest G. So for example, you can have a formula AXBY. So AXBY, for instance, it might be, A2B3. A2B3 might have lowest energy as compared to A2O or AB or AB2 and so on and so forth. So this for example, A2B3 may have lowest G. So basically what happens is that, and if these the phases, if such phases which have fixed atomic ratio, which means they will have their free energy curve is also very narrow. So, when you plot their free energy as a function of composition, so this is A, this is B, this is G. So, these phases have relatively narrow free energy composition profiling, and so if you plot for instance, this would be the free energy that is predicted by, for instance, so this is the, let us say, composition, this is where they have minima. So, this is what is the delta G, mixing, and this is nothing but G A, partial molar energy of A and B, and this is what is basically the, you can say this x naught is nothing but an sort of ideal composition, and given the narrowness of the free energy curve, it tends to have very little compositional tolerance as far as its own existence is concerned. So, Ax By literally means Ax By, it does not have any tolerance for extra A or extra B. On the other hand, you have a scenario if the, in which the phase has, so you can have a scenario phase with compositional tolerance. So, in such a case, the curve may be shallow like this. So, again if you apply so this is, let us say, x naught, this is delta G mixing, this is G A, this is G B, and this is the phase, but this is shallow, as a result it can have wider compositional tolerance. So, generally the shallowness of curve is determined by, so what makes this shallowness or let us say sharpness, okay, of G curve, what does it depend upon? It depends upon factors such as crystal structure, it also depends upon valence, it depends upon electronegativities, and it depends upon type of bonding between the elements, whether they have metallic or they have covalent or they have ionic. So, in general, compounds with metallic bonding will have more tolerance for compositional fluctuations as compared to compounds with covalent and ionic bonding. They are more stiff bonds with higher energy, and structures are far more stiff as well, and they do not allow too many composition fluctuations. Instead, when you change the composition, they tend to crystallize in different other forms. So, basically a narrow G curve signifies a phase called as intermetallic. Intermetallics are compounds typically with partially covalent or partially ionic bonding, as we have seen in structure of materials module. They are usually stoichiometric, and they have generally a fixed formula. So, you can have AMBN with fixed MS to N ratio. And there are examples such as intermetallics. You can have CuAl, CuAl2, CuAl, Cu3Au, CuAu, Ni3Al, NiAl. Various types of intermetallics are there. These are the compounds made from these atoms with fixed formula, and they have a very narrow G curve. And there are other compounds as well. For example, we saw in structure Leib's phases. Their examples could be MgCu2, MgZn2, MgNi2, and so on and so forth. So, if you want to look at these things further, go to the module 1, which is structure of materials, and you can find more details there. So, now these are the phases which can form in systems. So, you can have phase. So, in addition to solid solutions, you can have other phases which could be ordered phases, could be intermetallics. There is something called as line compounds with very fixed formula. Could be disordered phases. Disordered means partially ordered, let us say. And other structures, phases with other structures. So, there are various possibilities, and these are not the only possibilities, there are other possibilities as well. So, now we know that in real solutions things are a little bit more complicated as compared to ideal systems. They do not make extended solid solution all throughout. So, if it was ideal solution, what you will obtain is basically you will have if you plot free energy versus composition at a constant temperature and pressure. Generally pressure is kept at 1 atmosphere. So, we will whenever I do not mention pressure, it means pressure is constant. So, you will have, so this would be for example liquid phase GL. Similarly, you can have GS, which is the solid phase if it is a ideal system. If it is a non-ideal system, in that case, and it is the relative in this figure, it is the relative. Now, as you change the temperature, we know that the free energy decreases with temperature, and the shape of free energy curve changes and relative positions change. So, it is the relative change of these curves in the composition free energy landscape as a function of temperature, which will determine which phase is stable. For example, in this case I have shown GS to be lower than GL all across the composition range, which means solid is the most stable phase at this temperature. It might happen that GL is lower than GS in certain case, the liquid phase is more stable as compared to solid phase, but there will be instances where these two will overlap with at intermediate temperatures. At those temperatures, the two phase coexistence will come into picture. So, now let us look at phase coexistence in homogeneous systems. So, we will look at basically equilibrium in heterogeneous systems, not homogeneous. So, basically you have generally let's begin with binary systems. So, we'll just consider binary for the sake of simplicity. We'll introduce ternary later on. So, consider that you have two elements A and B which are mixed, and how these A and B mix with each other and how they react with each other, what kind of solid solutions they form, what is the free energy profile, that will determine what will exist under given set of conditions. So, let us say A and B do not have same structure and there are size differences as well. Now, these two, if these are the things, we need to be able to draw. One needs to draw the free energy versus G versus X curves for various phases separately, and then analyze how they move with respect to each other as a function of temperature and pressure, and then analyze the. So, let us say we have at constant. So, at constant temperature and pressure, let us say we have two phases, we have two components A, B, okay, and stable form of pure A is basically, it is the stable form of pure A to alpha phase. They assume structure which is FCC, whereas the stable form of pure B as well as the terminant solid solution beta, which is B rich phase, will assume a crystal structure which is BCC in nature. And then we will look at how the free energy versus composition plots of these two phases, these two components and phases look like, and what happens to free energies of A and B when they are at pure A and pure B, and when the composition is changed on respective side, A to B or B to A. So, now if I plot the free energy of a particular phase okay. So, if I let us say draw a free energy curve for a particular phase, let us say this is some phase, okay, and the rule of mixtures gives me free G. So, this is G A in that phase and this is G B in that phase for a composition X naught. This is the G of mixing 1 and this is the mixture 2. So, this is, let us say, instead of writing G mix, let us just write it at G1. This is G2 and the difference is delta G mix. So, this point here, let us say this is point A and this is, let us say, is point C. Okay. Now, this point signifies the basically we have said that beta phase has with BCC structure, this point signifies alpha phase with FCC structure. And so, let us say this is for BCC FCC structure. If you had FCC structured beta, then this would be, let us say, is the point B, and this would be the, so this will correspond to beta phase if it was FCC, and this is the difference between the two phases for beta and we need to draw in this case the free energy curves for both the phases. So, for both so this is sorry I am sorry, this is alpha phase. So, this is, let us say, G alpha. So, this is G A alpha, this is G B alpha, okay. And so this alpha phase we know is FCC structured. So, this is pure A in FCC structure. This is pure B if it was in FCC structure. This is, and since we know that B is a pure beta, which is pure B, is BCC structured, the free energy of this phase is lower. So, in fact, if it was FCC, its free energy is raised by this much amount. So, now what I need to do is that I need to draw the free energy curves of both the phases. So, when I draw the free energy curves of both the phases, XA and XB. So, this is, let us say, for alpha, and this is, let us say, for beta. So, this is G alpha, this is G beta, sorry, subscripts I can, G alpha and G beta. So, this point represents A, which is G A alpha. This will determine G B alpha. This will determine G B beta, and this will determine G A beta. So, now you can see clearly, because the equilibrium structure of pure A is FCC and alpha being FCC phase, the free energy of A is lower than that of free energy of A in alpha is lower than that of free energy in beta phase, which is BC phase, as at the pure A. Similarly, at pure B, the free energy of BCC structured B, which is beta phase, is lower than that of FCC phase of B if it was crystallizing in that. So, you can see that for both pure A and pure B, for pure A FCC is stable, and for B, for pure B, it is the BCC that is stable. Now, what happens intermediate compositions, that is what remains to be seen in case of equilibrium between the two things. So, just a modification you want to make here, that here it was in this figure it was GB alpha. So, if this was G alpha, it would be G alpha and GB alpha, and but since beta phase with BCC structure is more stable, the free energy of that phase will be lower, and that is what we saw in the next slide. So, we will stop here. So, what we have done in this lecture is we have just defined various phases like disordered intermetallic phases, what they are, how they are. So, how does the free energy composition plot, the shallowness of the plot changes as a function of whether it is a fixed compound or whether it has a composition tolerance. And then we looked at the free energy composition variation for different phases, which we will extend further in the next lecture. So, we will stop here. Thank you.